Okay, so welcome back to another video. So in today's video, we're actually given a limit, but actually it's not necessarily just the limit itself, but we're also being asked to determine the values of alpha such that the limit as x approaches 0 of 1 over x squared minus 1 divided by x times cosine of alpha x quantity squared is equal to -9. So it's just a little calculus problem. Well, we're going to be dealing with some algebra. There's also a couple of trig identities we're going to be using to help reach our goal to find our alpha values such that this satisfies the given equation. So with that, let's start. Obviously the best way to do this is with actually factor out 1 over x squared. In case you noticed, there's a x squared, there's an x and then the quantity and then square that, so we can just factor that out. So I get that this is the limit as x approaches 0 of 1 divided by x squared, then multiply by 1 minus, let's see, so this means this would be cosine square alpha x. Okay, that's the denominator, and then just divided by 1. So now let's note something. Let's note that secant square x, so we'll be using some trig identities here. We know that secant square x is actually equal to its the reciprocal of the cosine function. So it's secant x squared is equal to 1 divided by cosine x. But also another trig identity I want to use next is that tangent x is equal to sine of x divided by cosine of x. And then one more to use that's a pretty good measure to use here. So use the identity that secant square x is actually equal to 1 plus tangent square x. Okay, so we got our following 3 identities we're going to use. This identity won't come till later, but for now, we can actually use this identity to rewrite some of our expression of the inside. Okay, so with that, this means I can rewrite this as, let's see, the limit as x approaches infinity of 1 divided by x squared. Then this is, let's see, this is 1 minus, let's see, 1 over cosine x, so we squared that. So this is secant square alpha x, okay? And then, let's see, rewrite this a little bit. So same thing, the limit x approaches infinity of 1 over x squared, and then I'll replace the 1 minus secant square alpha x with this little identity over here. I'll replace this with this will be negative tangent square of alpha x. Okay, good. And so far, we established that's actually set that it's equal to -9. Now, we'll be using the identity where we set that tangent x is equal to sine over cosine x. So let's see, rewrite this a little more. That means we have that the limit as x approaches 0 of 1 over x squared, then multiplied by sine square of alpha x divided by cosine square of alpha x, and then just distribute the x squared into here. So we have sine square alpha x, and then divided by x squared cosine square of alpha x, and then so far let's just equate that equal to -9. Now what I can do now is that I can factor out a sine square alpha x and then an x square x, and then it comes down to there's a little neat limit identity that's actually comes out really nice. So let's let me first rewrite this. So we have that this is the limit x approaches infinity, and then I'll say that I'll factor out the sine square alpha x and then x square, but I can actually factor that out against, really it's just a quantity square, so rather I'll just write it in this sense, alpha x and divided by x and then that's square, and then multiply by, let's see, this is 1 over cosine square of alpha x. Okay, so it's nice. Now, here's the little identity that we're going to be using. So note that the limit as x approaches infinity of sine of alpha x divided by x is actually just equal to alpha. In a similar proof, it's very close to when we're evaluating like the sine of x divided by x is equal to 1. So it's just a constant of its input that's equal to the limit here as x approaches 0. It's pretty much the proof that I did where we evaluate this little limit, well, minus the alpha, but instead you don't use L'Hopital's rule. You actually use your sketch of the quarter arc of the positive quadrant, and then you usually use that use those lengths to help. Well, with the triangle included, use those lengths and then use those comparison to help evaluate this proof using that equality. Basically, I can actually just leave the link in the description below if you want to check out that proof. It doesn't deal with some constant alpha, but it actually just deals with like just alpha is equal to 1. So sine of x over x, and then you take its limit as x approaches 0, and then you get that as equal to 1. I can just leave that in the description below if any of you guys want to check that out. Okay, but anyway, this is the little identity we're going to be using to help evaluate this. So we note that, let's see, I'll just rewrite the same thing. Sine alpha x divided by x, 20 squared. And then I'll also take the limit as for this one too. It's basically just because of convergence and continuity. So let's say this is 1 over cosine square alpha x. Okay, so we know that this is actually going to equal alpha square. So this is alpha square multiplied by, now when we take the limit as x approaches 0 of this, note that cosine of 0 is always going to equal 1. So no matter what your choice of alpha is, it's always going to remain, the constant is just going to equal 1. So therefore, this is just going to equal 1 itself. This limit evaluates to 1. Okay, therefore alpha square minus alpha squared times 1 is equal to 9. And I accidentally skipped a step where negative tangent x, you can just factor out the negative and then just divide it by both sides. So really over here, this should be a positive 9 over here. So positive 9 and 9 over here. Okay, and then we're just about done. X squared or alpha squared is equal to 9. Just take the square root of both sides and you get that your values of alpha is just equal to positive and negative 3, like so. And there you have it. All right, now that's pretty cool if you ask me.